Okay. We're good to go, right? So today we discuss Berezin integral. First, so we want to just to integrate, to introduce integration of, well, first, if we have a supermanifold whose underlying topological space is just some open neighborhood of Rm, so at least we want to integrate somehow, well, locally, meaning that we want to integrate functions in here. Maybe let's even start with m equals 0 and n equals 1, just to see what properties of just usual integration we would like to make our defining properties. So if m equals 0, n equals 1, then so I need to take function f. So it's from C infinity 0, 1. Well, 0 means it's just over point, right? Well, basically this is just R of theta minus, right? Which is just R of theta, such that theta square is 0. Right? So we have something where, well, here I need to make this notation. So I need some definition for what I would like to call this thing. Right? Well, first of all, this should be R linear, and I would like this to be really a number, right? So we want R linear map from where to where? Well, it is symbolically may be denoted like this, right? So this is R theta minus to R. And the property that we would like to keep is that integral of derivative should be 0. Right? So such that, well, the only derivative that we can have is with respect to theta here. So we would like this to be 0. Well, some maybe some motivational just idea for that is that there are no odd like physical odd points, right? And so therefore there are no boundary, and so therefore integration over derivative should be 0. So odd dimensions kind of are not physical dimensions. And so therefore there's no boundary. All right. So once we have this, then we actually fix our integral up to constant, right? Because so this C01 star is actually two-dimensional, right? And so we just need to write integral over of something like this, C0 plus C1 theta d theta. And well, it should be proportional to C1, really. Well, let us just choose normalization such that it is just C1. Right? So the reason being is that actually C0 is actually C0 theta d over d theta, right? So therefore it's a derivative, but this one is not. And it's linear, so therefore should be proportional to C1. So let's make it, let's fix the normalization, so this is just C1. All right, so this would be our definition for C infinity 0, 1. Well, if we make still m equals 0, n equals just any, then we just extend this definition by using, like, if my, like, by splitting the variables, so to say, right? So if f is from, well, r theta 1 theta n minus, then I just put, so I still write the same symbol in this case, f d theta, but I have like multiple thetas, or sometimes just I can write d theta 1, d theta n. Well, maybe this one is better because it really depends on the choice of order of thetas. So, but again, it's just up to minus sign, it's all the same. So these are just notations, right? So if my, so I just fix this by saying that it is, again, R linear, and also if I have the product f theta 1, f of theta, wait, I don't know, f1 of theta 1, f2 of theta 2, and so on, fn of theta n. So this is just product of integrals f I theta I d theta I from 1 to n. Right, so this is actually fixes integral for us for well, here I should also write, I guess, so well, here I don't have to write anything, but okay, this is like should be a point here, right? Really, so it's integral over manifold, which is just one point in this case. But if it's not a point and still m is not 0, then well, it's clear what I have to do. So this should be generalization of just usual integral. So if m is not equal to 0, we choose some orientation on U. And with this choice of orientation, if I take f from C infinity of U, tensor R theta 1 theta n, then I can define what is f f, integral of f. So, well, I need to write down f, it's a sum fi theta I as usual, no, our usual notation. But I need to split out the term corresponding to for I being like the set of all numbers from 1 to n. So usually I think it's denoted like this, right? Maybe. So no sum here. And sum here over I, size of I less than n. Right, so if I write f like this, then I just, and also I would like to take, to have the condition of on fn that it has compact support on u. Then I actually define integral over u f dx d theta to be integral over u. Well, here I should maybe write mn to emphasize that this is super manifold. But this is just the usual integral of fn dx with a chosen orientation on u. All right. So this is, well, as easy as it is on just locally, it's like that. And the funny thing, usually what people always notice is that integrations really, well, it's derivative with respect to thetas. So actually integral is the same as taking, well, in this case, in case when m equals to 0, like just funny fact for you, integral is the following thing. So it's d over d theta. I should start with n, d over d theta n minus 1, d over d theta 1. Right? So like that. Okay. Now I would like to, so okay, so my goal is then to go and maybe define things over what I want to integrate if I have you know, globally, right? If I have super manifold and glue it out of super domains, so what should I integrate at all and how? For that, I really need a change of variable statement of local, right? And for that, I need some kind of Jacobian. Let us introduce it. So, suppose that I have isomorphism of superdomains. So let phi, so this is from UMN to VMN. It's an isomorphism of supermanifolds. So if I write let, it should be B. Okay. Then let me just choose some super coordinates here, super coordinates here. So the first one would be x1, xm, theta 1, theta n. So these are coordinates on u, mn. And on the second one, we have y1, ym psi 1 psi n. So these are coordinates on v mn. And let me consider the pullback of y with respect to phi and of psi with respect to phi. So I'm just introducing notation. So fi is a pullback with respect to phi of xi. Right, and let me denote gj. It's a pullback with respect to phi xi j. So it's just denote. It's notation. And let me form a matrix. First of all, let me consider this matrix, df over dx. Well, it's a Jacobian matrix, so this is just the ijth element of this matrix is this guy, and it belongs to a function on umn, right? So it has thetas also inside. Yes, so might have thetas because when I pull back, it also can have like even elements consisting out of this as well, right? So sorry, so this is a matrix. This is one thing, and well, then I have this similar notation for 3 more things. So I have df over d thetas, dg over dx, and dg over d theta. So these are matrices of corresponding size. So this one is m by m, this one is n by n, and these are rectangular. Then I define the following matrix. J, let me call it J phi. So this is like a block matrix consisting of these blocks, but I will need to put additional site in this corner. So actually there will be df over dx here, then df over d theta, but here I have to put minus sign. Then dg over dx, dg over d theta. Yes. Right. So such thing, and of course I can multiply this as matrix. So all these guys, they live in a supercommutative algebra, right? So this is like a, well, okay, so this matrix corresponding with elements from supercommutative algebra. In particular, we know how to compute Berezinian of this, right? Moreover, so we have this even, and these are odd elements, right? So that's exactly what we computed Berezinian of. But before computing Berezinian, let me maybe formulate proposition which explains this weird minus over here. proposition. So suppose that I have two isomorphisms now. First one is our phi, and the second one, say psi, and it goes to WMN. So I'm fixing three set of coordinates now, but the set of coordinates that I fix for phi here and for psi here is the same here. That's the only consistency that I need. Then, well, because my matrix J depends on these coordinates, right? So that I should be said. Phi and psi isomorphisms, as before. Then I claim that if I the composition corresponds to multiplication of Jacobians. All right, so should be written like this. So composition should be a little bit accurate. So I have to take J psi and then pull it back with respect to phi. This will be an element in here. So will be a function in here, and I can multiply it by a function in here, which is J phi. This is the same as J psi phi. Okay, I will not prove it because, I need to make some problems for homework, and this one is just a useful check. So this can be checked just by you need to see what how the matrix is multiplied. So you need to interchange a couple of elements there, and this minus compensates. So matrix, you can really in the chain rule multiply matrices without any signs, right? So it's proof homework. Ну, наверное, в J на данный момент, видимо, нет. Да, на данный момент не важно. Но вот я сейчас захочу Березинян от этого взять. Вот. И да, здесь, наверное, здесь не важно. Да, давайте сотрем. Ну, там, если это не изоморфизм, то можно, в принципе, другие какие-то размерности здесь брать. Да, ну и чтобы там здесь согласовывалось, мне нужно. Ну, то есть это можно как-то еще более обобщенно писать, да, чтобы они там перемножились как надо, эти матрицы. Все. Окей. Ну, не, в принципе, да. Ну да. Okay, done. Okay, for now it is indeed not needed, the fact that it's isomorphism, but in the following theorem it should be isomorphism. So suppose that phi u m n v m n isomorphism. Then and F is a section of our structure sheaf on U on V. So it's from C infinity Mn V. Also, I would like this to have. Well, when I write this, C, it means its component, which is Fn, has compact support on V. All right. So this means compact. So Fn has compact support. Because I would like to integrate this thing, then then ну, а сейчас 0 или не 0, ну, сейчас, ну, вылезет. Не, ну здесь какой-то одной, но вот сейчас мы придумаем теорему, сейчас мы еще не сформулировали, но что как бы должен еще Березинян вылезти, да, при переходе. И он как бы все компенсирует. То есть, ну, не, ну это правда, что там может чего-то при переходе. Это правда, да. То есть это правильное замечание, что при переходе там будет играть значение f и ты, где и это не вот это вот n. Вот. Но, значит, будет ли такое, что в какой-то карте, значит, у нас fn 0 вообще везде, да, на fu. Ну, даже можно точку, да, брать. Ну, может быть. Может быть, да. Да, но при этом, значит, сейчас. А как там... Ну хорошо, вот теорема формулируется так. Давайте я допишу. Интеграл по v, значит, так, then integral over v f dy dxi. Well, we keep the same notation for coordinates. Is integral over u phi star of f Berezinian of j phi dx d theta. Ну да, если он, значит, видимо, 0, fn не 0 в другой карте, ну, то он добьется до нуля как бы здесь в Березиняне. Значит, когда мы его вычисляем, там все равно, то есть он, конечно, четный получается, Березинян, но все равно там могут быть тетасы. Да, вообще-то говоря, да. Да, там могут быть 3, да, это только в этой карте. Ну, да, это правда. Then we should change it to this. Yes, that's true. Okay, thank you. So let's try to prove this. So proof. Um, right. First of all, as usual, I will denote by J. It's the ideal generated by thetas. So generated by theta I. So it's ideal inside C infinity Mn U by theta I from 1 to n. All right. Then I claim that it is enough to prove the theorem in the following two cases. So it is enough to prove theorem in the following cases. Case number 1. So I have my f's. So I keep this notation, right? So this is my phi, and fi and gj there as like that. So case 1 is that one of f's is trivial, is non-trivial, but it's just say first one. So f1 is actually by the way, here I need to put y, right? So here I need to put y because I'm pulling back and this coordinates on v. But f1 should be x1 plus something that I will denote by gamma, where gamma is inside, well, j, even j squared, right? And this is the only, and then the rest of fi's are just xi, and the rest of gj's are just theta j's. This is for I from 2 to m, and for j from 1 to n. So this is case number 1. Case number 2 is that I change only one g, and the rest of coordinates, so to say, are not changed. So my my g1 is some, well, it should be theta 1 plus something that I will denote by eta, and eta is inside j cube. Plus, well, and also the rest do not change. So I have fi is xi, and gj is theta j, I from 1 to n, j from 2 to m, from 2 to n. So I claim that's enough to prove for these two cases. Now let me justify this claim, why this is true, why this is enough to prove for these two cases. Well, So proof of claim. So what in general my fi might look like this. So this is like some constant, maybe which does not depend on thetas or x's. Plus, so I'm expanding also like as a Taylor series in x's, like even a constant term, right? So it has like constant in thetas, I mean. So ci plus maybe something like aijx j, so linear term. Ну да. Окей, тем лучше. So, like that. Ну, у нас открытый компактный носитель. Сейчас, извиняюсь. F никак не связано. Вот это F никак... Ну, это плохое обозначение просто. Вот это F никак не связано с вот F-итами. F-ит это чисто фи. Это плохое обозначение. Ну, так что все-таки, ну, то есть я, в принципе, мог бы взять области, и она центрирована не вокруг нуля могла быть, а там где-то. Вот, поэтому все-таки есть что-то. Могло бы быть. Ну, я не знаю, ну, пока что, раз уж мы это сказали, ну, наверное, не будет больше непонятки с этой стороны. Давайте не будем пока менять обозначение. Alright. So then, so plus something more, well, I can, you know, denote it by Ri of x. So this is of degree greater or equal than 2 in x. Let me just say this. And plus another thing, which is Ri tilde x. So this one is inside j square already. So this I just decomposed in the Taylor series the constant term, and this is what depends on thetas, right? And gj, well, I can write down in a similar way. Maybe let me take gi as well here. So this will be well. This one will not have a. So like I'm kind of decomposing now in terms of thetas. So I will have bij, but bij will depend on x, so to say. Theta j, right? Plus something. I don't know. Let me denote it as si. But this one is already in j cube. Okay. So I have this. Then my d. So let me take my phi and consider well differential of phi at some point x in u. Right? Well, I just want this notation. So if we actually computed it last time that it has block form, and here I have zeros, and here I have something, phi 1, maybe phi 0 rather, of x, and this should be like phi 1 of x. Since it's isomorphism, these two blocks are invertible. Right, so this is like actually matrix over R, right? So these two blocks are invertible. In particular, B here. Well, again, I refer to the previous lecture. So this matrix Bij, I don't know. Let me call it B. Well, this is actually, I already called it somehow. It's phi 1 of x. And the matrix A, which is actually constant, but so A Ij. So this is just phi 0, but of 0. All right. And so at each point, phi 0 and phi 1 is invertible. So this is invertible. And this is invertible. So I can now, let me just consider isomorphism again of super domains, well, from UMN to UMN. So this will be just linear in x and theta. So to go to this, I just need, some linear transformation first, really. So this will be, well, at least linear in a certain sense, right? So we have well, let me really just maybe one of them, let me make one of them to be U prime Mn. So let me think of this copy like it is different copy of all right. So then and on U prime I will have coordinates x1 prime blah 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 x n m prime theta 1 prime blah 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 theta n prime. Right, so these are coordinates in here. What I want, yeah, so I want to define psi. Yes. And I just define it like this. Psi star of x I is negative ci plus some aij inverse xj prime, and psi star of theta j is some bij inverse at x of x theta j prime. Sorry, maybe something is wrong. Maybe this one should be I. Okay. So I defined psi star like this. And then my j psi will be what? J psi. So I will still have, so let me see. So it will be determinant of A here. Well, determinant of A inverse, right? well, no determinants, so just A inverse here, right? B inverse in here. And then in some block where I have derivative with respect to x, I think something here and 0 here, I think like, right? Because d, so this is my g in the notation that I just erased. So dg over dx is still something, right? Что-что? Там не 0, df. Вот в этом 0, а вот в этом не 0, да, вы говорите? Хорошо. Это меня тоже устраивает, потому что я хочу теперь березенян от этого посчитать. I want to compute Berezinian of this, and this is really determinant of A inverse. So this of A inverse times the determinant of B, right? The Berezinian of this is this thing. All right, so let me now take and compute integral. So let me take some f, I don't know, or f or g, so bet notation, so maybe h. So h is in C infinity mn of u prime. And so then I would like to consider this psi star of h integral over u mn Berezinian of j psi d x prime d theta prime. I want to compute this. I would like to see that this is really integral over h dx d theta. That's like a h. Сейчас, давайте разберемся. Значит, координаты с штрихами на u штрих. Когда я полбэчу, да, когда я полбэчу, я, значит, получаю... вот это на u, правильно. Вот так. Интеграл получается все-таки... интеграл по u штрих, да. Угу. Yes, okay. Very well. So let me now compute this. Well, Berezinian I computed, and so this will be integral. I have h sum over I, hi of a, well, maybe I even have to put like c, small c here, right? Of a inverse x, right? So I'm applying psi star to h. So it will be like this, and then b inverse theta I. Right? Okay. And this integral, so then I have Berezinian, which is determinant of A inverse, determinant of B, and this is still, well, dx d theta primes. And so maybe I have to put primes also here and here, right? and also this is over u prime mn. Dx prime theta d theta dx prime d theta prime. Let's see. So I need a term here which is which gives me, I don't know, theta prime 1, theta prime 2, and so on, all the way to theta prime n. So this gives me really determinant of B inverse right here. So I continue here. So this is integral. And I still will have hn, right? Like this. So still the input will be from only from hn, because this is linear in thetas here, right? All other terms will be a small degree in thetas. So hn, then of what? Of A inverse x prime, then determinant of A inverse, and then, well, determinant of this B inverse will cancel with this determinant B, because yeah, so just because determinant of B inverse is the inverse of determinant of usual matrix, so we have just like that. Well, but only we need now dx prime, right, and integral over u prime. But this is just a change of variable in just usual integration. No absolute value here in Jacobian, so because we have orientation right on u, and so this will be integral over u now of h n of x dx. Well, which is just integral over u m n h dx dθ. So for this simple psi, we proved our theorem. Well, okay, I lied that there should be only these two cases. There's a third case that we just checked, where psi is like that. Okay. But now, if I now compose phi and psi, so my phi has this f's and g's. Well, not well. This is what I want, but my phi has not this f and g's, but like that, like in the proof of claim. Then I have so this I erase. So let me take phi tilde, and this is composition of phi and psi. Then phi tilde of or pullback of phi tilde of yi is actually xi plus some gamma I, which is in well, which is in J prime. Oh, J prime is clear what it is, right? So just a symbol notation, but we were in U prime. And this is for I from 1 to m, and phi tilde star of xi I is actually theta I prime plus some eta I. where eta I is in J prime 3. Well, this one is even in the square of J prime. All right? We have now the linear term is what we need, right? We just need to break this down into smaller, into these cases. But I claim that phi tilde is a composition of morphisms of the form 1 and 2 there. Well, of course, maybe it shouldn't be like the first that changes, maybe, but only one coordinate changes of the form 1 and 2. Well, some care should be taken here. So when I compose, I still, let us rather see an example. This will show what I want to say. So for example, suppose that I have maybe my phi, phi tilde, right, is x plus gamma. Maybe so this is for R or U 1, 1. So phi tilde of yi star is, well, maybe not yi, but just y. I have y, and I have xi. So suppose that we have this. Right? How do I break this down into two morphisms? One of the form 1 and the one of the form 2. Well, I have, of course, I would like, I would like phi 1. Well, I will have one additional set of variables that I again denote by primes, right? Since I break this into morphisms, right? So phi 1 is the one that I apply first. Is the one that I apply first. So this will be phi 1 of y is x prime plus some gamma. But this is not this gamma, should be gamma tilde. And phi 1 of xi is just theta prime. This is the first morphism. My objective here in this example is to show that in the composition what I add is not necessarily what I add here. So I did little, modification to that. But they still will belong to the same, to the ideals that I need. Okay, that should be little accuracy is needed here. So this is phi 1 and phi 2. It should eat, well, again, this is star. Phi 2 star does nothing with x prime, meaning that it maps it back to x. Right? And then and phi 2 of theta prime. So this gives me theta plus eta tilde. So I need to figure out what is gamma and eta tilde. Let me just compose phi 1 and phi 2 then. What do I get? What do I get? So, okay, let me just erase this. all remember the cases. It's not hard to remember. So when I compose, I get what? Phi of, first I apply phi 1, then phi 2, right? If I apply this to y, what do I get? First, I will get x prime gamma, and then x, so I get x plus phi 2 star of gamma tilde, right? And phi 1 star, phi 2 star, if I apply it to psi, so first I do nothing, theta prime, and then theta prime goes to theta plus eta. So it will be theta plus eta tilde. So it means that eta tilde is eta. This is one is easy, but gamma should be phi 2 star of gamma tilde. And since phi 2 is really morphism, since this guy was in J, this one is also in J squared. Okay, so some accuracy is needed. That's what I want to show by this example. So, but well, I'm interested in figuring out what in eta tilde, right? Since I know what are gamma and eta, so this is my phi tilde. Well, here I should take gamma tilde to be phi 2 star inverse, right, of gamma. So this I know that it's in J squared, so therefore the whole thing is in J squared. Maybe I need to put primes somewhere, but I'm already lost where I should put primes, where I shouldn't, but okay, just not very important. Okay, so we all agree now that we only need to prove these two cases. Let's prove them then. So first, let's prove of case 2. This one is easier than 1. Proof of case 2. So I have well, f i's are x i's, and g1 is theta 1 plus eta. Right, so I had this is my case 2. So I take eta to be, I can write eta to in the following form: theta 1 beta plus alpha, where both beta and alpha, they are in C infinity of U tensor R. Well, there are no theta 1 in them. That's what I mean. So tensor R theta 2 theta n minus. Right? So if I do like that, then well, I can compute the Jacobian matrix. This would be, if I'm not mistaken, the following block matrix. So I will have once just identity matrix here, and here I will have 1 plus beta. Right, because I have, this is derivative with respect to theta 1 stays here. G1 with respect to theta 1. So 1 plus a derivative of this is beta. But then something, I think something here, I don't care too much about. These are derivatives of eta with respect to other thetas. And ones are here, and then zeros everywhere else. Think like that. So the Berezinian of J phi is just 1 plus beta inverse. All right? And 1 plus beta inverse, and this inverse exists, by the way. Well, it because no, I mean the Berezinian exists, but this is just beta starts. Beta contains some theta, so it's really nilpotent. So really, we can invert this. All right. So Berezinian is this one. Then I just put this into my computation and check. So what do I have then? I have integral. I need to pull back of my test function. Okay, let it be h, not f. Not to confuse with our f coming from phi. So we have Berezinian of j phi dx d theta. Right? So is it dx d theta or okay, so f, well, my h is in v, right? So it's inside c infinity mnv, right? So h is written like that, sum hi of y's and then psi I. So h should be written like psi. When I pull it back, it will be in x and theta. And Berezinian is in x and theta, which is function on u, rather. All right. So when I have this just equal to integral h corresponding to the top term there in h, so hn of x dx times integral of theta 1 plus beta plus alpha. And then I have theta 2 blah 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 theta n, right? Because I'm pulling back psi, right? So when I'm pulling back psi, right, psi 1 becomes this, and the rest of psi's then becomes just thetas, right? So I'm pulling back psi. So this is from pulling back psi. Then I need then I need Berezinian, which is 1 plus beta inverse. And then I integrate over thetas. Почему аж и ты не вносит вклад? Потому что в y мы никак не изменили. У нас кейс 2. Изменили мы только тета первый. ам, м, Значит, ну мне обязательно нужно слагаемое. А, а, м. Действительно, у меня в бета, сейчас подумаем. Значит, у меня в бета есть, в принципе, какие-то там тета-2, там тета-3, да? И вообще говоря, и в альфа тоже. А, и вполне себе, если они здесь отсутствуют, да, у меня могло быть такое, значит, тета-1, 1 плюс бета, плюс альфа. Ну, значит, я, во-первых, делю вот на это, поэтому в любом случае, да. То есть, если тета-1 нету, то в любом случае плохо. То есть у меня должно быть тета-1 содержаться, правильно? Если тета-1 содержится, то у меня есть вот такое слагаемое, но еще в любом случае у меня такое есть. Значит, это будет тета-1. Тета-1 плюс, значит, альфа. Плюс альфа на единичку плюс бета в минус 1. В них тета-1 нету. Ну, а если у меня есть тета-1, то должно добиться как бы тета-2 и так далее. То есть вроде бы больше никаких вариантов нету. Вот. Ну, действительно, это вы правы, то есть я проскочил и, видимо, даже не обратил внимания. Так, ну проверили, что действительно только HN. Окей, let's continue. So right, so we then have what? We have integral hn of x dx, then term theta1, theta blah blah blah, theta n d theta, right, which is just 1. And plus, so there is no theta 1 in here, right? So plus alpha times 1 plus beta. So maybe the only thing... ну вот это, значит, штука, где я как бы дополнительный тета-2 получаю, я только из тета-1 могу. Вот. То есть если я как бы, если у меня тета-1 присутствует, я это получил, да, то у меня как бы уже ее нету. То есть, ну, я из тета-1 получил, а здесь уже ее нету. Да. Так что да, действительно, окей. So then I have this times, so plus maybe integral of this times theta2 blah 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 theta n, right? But this one is 0 because that's theta 1. And this one is really what we want to get because this is integral of h of x. Sorry, it should be, well, here I just, so this is hn of x dx. Well, so here is just x and y is the same thing, right? Because of case 2, right? X and y, they're the same variables, right? So this is really h of y dy, hn. But I can write this as dy d psi, and I'm done. So this is the proof for the case 2. У нас кончилось время, да? Ну ладно. Давайте не будем прям... Давайте это оставим тогда на следующий раз. Угу. Ну да. Ну, нет, вроде я не хочу, чтобы зависели. Мы сделали линейную замену, и осталось что-то, да, ну может быть не от это зависящие, да? Да. Ну, действительно, мне нужно тогда сделать следующее. Мне нужно, чтобы... ну, А и Ж все равно у меня как бы появятся в... Значит, мне, да, нужно исправить следующим образом это, правда. Значит, мне нужно пси сделать таким, что пси от... Ну, у меня есть фи с волной, да? Вот я всю его должен использовать, вообще-то говоря. Да, то есть пси со звездочкой x, это фи с волной в минус первый от y. Да, тогда на координатах, да. Это я, конечно, зачем? Ну да, действительно, это вот мне вот так надо исправить. Ну там просто замена координат, ну там будет якобиан обычного перехода, да. Ну да.